one of the most basic ways of solving Schrödinger equation with a numerical method is using this method that we call the shooting method. So this kind of shooting method is actually a class of ways of solving differential equations with a numerical way, where it's something like an analog of if you want to find some kind of trajectory for a bullet, for example, you can shoot the bullet with different angles and different velocities until you reach this trajectory that you want, right? So this is more or less like the analog would be, you are looking for some kind of wave function. For example, in Schrödinger equation, you're looking for a wave function that converges as the x coordinate goes to infinite, for example, so that the function doesn't diverge. Then you are looking for, you change the energy of the system until you find a wave function that behaves like that. That's more or less the way you are going to solve Schrödinger equation here. And then keep in mind that what I'm talking about is the time independent Schrödinger equation, okay? So I'm just talking about the eigenstates of the system. So how is this going to work? Let me start writing the Schrödinger equation. This I'm going to do only for a one-dimensional problem, okay? So the Schrödinger equation would be something like that for the one-dimensional problem. And then I have a potential that it can be even arbitrary here, but I'm going to use this as an example just as a square well, but you can put whatever you want here in this V. There will be one condition only, I'll talk about that later. But the equation will be like that. And let me also use coordinates here and energies that I will call like V bar, E bar, and so on, because these have units for them. And then this is X bar also. Now, what I'm going to do is a substitution here that I normally do when I solve Schrödinger equation, is to make these things all like dimensionless. So then I can always substitute this combination of constants by the Rydberg energy multiplied by the Bohr radius squared. So I like doing that because then I can put this Bohr radius inside the coordinate, the spatial coordinates, and I can divide everything by this Rydberg energy. So in the end I'll have like Rydberg energy here, Rydberg energy here, and then I don't need to put this here anymore. And as I put this A0 in this coordinate here, then I don't need this A0 square anymore. So in the end your equation is going to be in a dimensionless form. It will look like this, plus V psi is equal to E psi, where the coordinates now, this X coordinate is actually the real coordinate divided by the Bohr radius, and the energies and the potential is going to be divided by the Rydberg energy, okay? So, I mean, this is V, of course. Then it will be something like that. So this is the equation that I'm looking for, that I'm trying to solve, right? So the idea is, if you have any potential here, let's write it, let's say, for a square well, but it can be also a parabola or anything like that, but there is a condition that is, at least for the way I'm going to solve here, the potential has to be an even function. Because then if a potential is an even function of the coordinate x, then the solutions are for sure either even or odd. You can prove that mathematically. So I can do that in another video. But let's say that you have, for example, a square well potential. So you have something like this. And I'm going to solve this thing only for the positive part, because then the positive x part, right? Because the negative x part, of course, it's the same, but if the wave function is odd, then you put it as a negative of the positive one. Otherwise, you put it as exactly as the same as the positive one if it is an even function, right? So I'm going to choose classes of solutions that are either even or odd solutions, okay? So, but before that, let's just see how I'm going to solve this problem here numerically. So what I want is the psi in every point here, right? And I want this psi to be something like, something that converges as x goes to infinite, right? So it can be also something like this, for example. It could go like this and converge negatively like that, right? And it can also be an odd function like this. Let's say it goes up and then down. It could also be something like that, right? So these are the functions that I'm looking for, but the important thing here is that they need to converge as x goes to infinity. So if I choose any energy here, I'm always able to find a wave function that fits, that suits this equation here, you know. So for any energy that I put here, I can always find a psi that satisfies this thing. But the problem is this psi is going to be, it's not going to satisfy this condition that it converges, you know. So this is the main point of the method here. So, but okay, let's talk about the method itself. I mean, this is just this is something that we are going to discuss later on in more details. But let's start talking about the procedure itself. So I want to see the wave function everywhere here. I want to calculate the wave function everywhere in this x. So what I do is I get this x coordinate and I discretize it in small steps, right? So each of these ticks I put here, these would be like x1, the next one is x2, x3, and so on, right? And as I said, I'm going to do that only for the positive axis. So then I have x1, x2, x3, and so on. For each of these points, I have a wave function, psi1, psi2, psi3, right? So it's not actually these are not wave functions. These are the same function, but in different points in space, right? So I associate psi1 to the point 1, psi2 to the point 2. In the end, this is going to be my function, but it's a discretized function now. This thing will be, if these were continuous, then I would have psi of x, but instead of that I'm writing it as a psi of I. Then it's now I discretized this thing, and the distance between these points in x direction, I'll call it delta x. And so now what I'm looking for then are what are the psi of 1, 2, and psi of 3, and so on, right? This is what I'm looking for. And there is a way of calculating that. I know what is the derivative of a function, right? The derivative of a function, I can write it as a limit delta x going to 0 of psi of x plus dx minus, I said delta x, but actually right now I'm using still dx. I mean, this one is psi of x, and I put a dx on the bottom here, and then if dx goes to 0, then this thing is the derivative. But I'm going to make it like approximately in my discrete axis here. I'm going to write it as psi of I plus 1 minus psi of I divided by delta x, and this is a good approximation provided that delta x is a small number, right? So then you have to discretize as small as you can in the computer. When you want to solve this thing in the computer, you can do that. So by the way, I didn't mention, but I mean, I guess you already have imagined that this kind of method, like numerical methods, needs a computer to be solved, right? And this one, the advantage of it is that you don't really need to know much about programming languages. You can solve this thing like with a very simple programming language, whatever you want, but you can also solve this like the way I'm going to show here. You can solve it using like Microsoft Excel or the Google Spreadsheets or the LibreOffice Calc. You can use it, these kind of tools that are not really like very complicated in terms of programming, right? And because the method is going to be very, very simple. So okay, so the derivatives will be like that. Then I will have psi of I plus 1 is equal to, I can like do this, rewrite this equation like this, right? Psi of I plus delta x, then the derivative of psi at the point I. This is the definition of the derivative, and I can find whatever is the psi in the next point using the previous point and the derivative at that previous point, right? But the problem is, and that this is where the equation enters, I don't know what is the derivative everywhere. So this is where the equation enters now. So this is one thing that you have to be able to solve, and the other one is the equation itself, Schrödinger's equation itself. So I can rewrite Schrödinger's equation this way. This is equal to V minus E psi, right? But then in this discrete space, I'm going to have something like the derivative of psi, or actually let's write it one more step here. Let's write one more step before we do it. This is the derivative of the derivative, right? So this I can write using this method here, like the numerical, this is what we call finite differences scheme, okay? So using finite differences, I get 1 over delta x, and then the derivative of psi at the point I plus 1, and the derivative of psi at the point I. And this is going to be equal to the energy, or V minus energy multiplied by psi at the point I, right? And remember that this V is a function of space too, so it's Vi here that I'm going to write, right, in this discrete space. So let's rewrite this equation somewhere else. Let me make another page here. So I will repeat the first equation just for organization, for the sake of organization. I'm going to write it like this, delta x, and then I'm going to, the derivatives, I'm going to start writing them like psi prime, okay? So now what I'm saying is psi prime at the point I plus 1, this has to be the psi prime at the point I plus delta x multiplied by V at the point I minus the energy and psi at the point I, okay? So now if I iterate these two equations, I am going to be able to find the wave function everywhere, right? So, but first I have to start with an initial boundary condition, right? So the boundary condition, for the boundary condition, I can choose that the wave function is either even or odd, right? If I'm saying that the wave function is even, then what I'm saying is, if you look at this drawing I did here, even functions would be the blue ones, for example, these ones that start with psi equal to 1 here, and then the derivative is 0. So I'm going to highlight also here the odd functions. These odd functions start from 0 and the derivative is 1, okay? So then let's go to the next page now. Let's define what are these conditions then. The condition is, if the wave function is even, it will start with psi of 1 as equal to 0, and the derivative psi of 1 is equal to, it's the opposite. If it is even, psi of 1 is equal to 1 and the derivative is 0. Now if the wave function is odd, then I start with psi 1 is equal to 0, but its derivative, psi 1 derivative, is going to be 1, right? Okay, this is what you are going to start with. And you also have to define an initial energy. This is the energy that you are going to guess, right? So you start guessing some energy and then you see how it goes, okay? So what I'm saying is, once you do that, let's say that you chose some energy and you chose an even solution. You want to find the lowest energy even solution, okay? So then what you're going to do is you say psi 1 is 1, psi 1 prime is 0. Then you substitute this thing here, psi 1 is 1, psi 1 prime is 0, and you will obtain psi of 1 plus 1, which is psi of 2, right? Now you already have psi of 2, that's fine, right? So now if you want to find psi of 3, psi of 3, you need psi of 2 that you just calculated, but now you need the derivative of psi at I equals to 2. How do you find that? You get psi 1, derivative at psi 1, and these are the initial conditions, right? You substitute here, you get the derivative at psi 2. With the derivative at psi 2, you substitute here, you get the function at psi 3, right? And then if you keep going on doing that, you see that if you want psi 4, you need the derivative at psi 3. But to get the derivative at psi 3, you need the function and the derivative at psi 2. And then you go on, then you find like psi 4, psi 5, psi 6, and then you can find all the psi's that you want in the with this condition that you gave, like it's a even function and the energy is given by this energy that you already chose there. If you do that, you probably didn't guess right what is the energy, right? It would be a very funny coincidence if you find exactly the correct energy that you need for your system, right? But what I'm saying is probably we are going to find something like a function that goes like this, and then it diverges, right? So it will be like that. And then that's because the energy that you chose is not appropriate. Let's say I'm going to get some numbers here just for the sake of, like, just for an example, you know, but just for you to understand more or less how it works. But the numbers that I'm going to give here are fake, okay? So let's say that the correct energy should be something like 10.523, and then it's always there is a, let's say, an infinite number I mean, you can get as precise as you want with this, right? So then you can put like more numbers here. Then this in milli electron volts, okay? So if you choose energy equal to 9, then it will be something like this. Then you choose the energy equals to 10, the wave function will be better. When you choose the energy equal to 11, then you see that the wave function now diverged to the wrong place. It diverged down now. Okay. Then you know, if you do that, you will know that your energy. This is the one that where you guess that the energy is 10. This is the one where you guess that the energy is 11. So you did it like that. So then you will know that it's the correct energy is in between 10 and 11. So let's put one more number here in your guesses, right? Let's say you don't try 10, you try 10.1. 10.1, you'll find something like this. 10.2, you'll find something like this. 10.3, 10.4, 10.5. Then you try here 10.5. 10.6 will go down to a negative value. Okay. So this tells you that your correct energy is between 10.5 and 10.6. So now let's start. 10.5, 10.51, 10.52, 53. Then in 4 it's going to go negative. Then you know that your energy will be something like 10 to 10.523. If you want to go on, if you make this axis longer, then you see, if you make the x-axis longer, you see that it's going to be harder and harder to get the correct behavior, like that the wave function does not diverge and so on. So this is your control for how accurate you want your energy to be. If you want this thing to converge even up to an x going to very, very large number, then you need to be very, very precise in the energy here. Okay, so this is something like, if you this is you who needs to be to give you how to understand how accurate you want this wave function to be. Okay, so I mean it can be that for your axis it's already like this, but then you increase the axis and then it starts to diverge, and that's because you didn't choose the energy like accurate enough. Then you need to be better in the accuracy. Okay, so that's the point. So this would be the method. So in summary, you you choose if the wave function is even, for example, or odd. If you choose that it's even, then you need to define psi1 prime, the derivative of psi1. This is going to be, the first one is going to be 1 and the other is 0. You apply these things to this equation, you get psi2. You apply here, you get the derivative of psi2. Then you apply the numbers here, then you get psi3, the derivative of psi3, and so on and so forth. Then in the end, you get a wave function like that. If you chose the correct number, it will converge. Otherwise, you have to go through this procedure that I said, like changing and changing the number little by little until you find the correct number, the correct energy that satisfies your equation. And this is going to be, once you find this energy, this is going to be the ground state energy of your system. Okay, I'm going to call it E0 so that you know that these indexes here are for even solutions. Okay, so now let's say that you found E0, right? But let's say that you put another, you want to go on, right? You increase even more the energy. If you increase from the 11, 12 and so on, then this thing will start to go like negative and more negative, right? But at some point you see that this thing will go negative and then it will go up again, right? And once it goes up again, sometimes it diverges to the positive side again. So now maybe you could go for some energy in between here, that you start with a solution that goes like this and diverges down, or you change a little bit your energy and get a wave function that diverges up, right? If you start the procedure again, like refining more and more your energy, you will find a second solution that converges also here. And this is a solution where you have a node here. You have a wave function with a node, and then it goes to negative, and then it converges. Which wave function is that? That's the next even state that you get for as an eigenstate of the system. And if you keep going on, then you find the third even state, which would be E4 and so on, right? So, and then where are the odd solutions like E1, E3 and so on? Of course, if I didn't choose an odd solution in the beginning, then they will not appear, right? So now I have also to do the same for odd solutions. I start with psi1 equal to 0, psi1 prime equal to 1. I substitute these things here, and here I get psi2. From psi2 I get also the derivative at psi2. Then I put it back here, and then I get psi3, and then the derivative of psi3, and so on and so forth. But now for odd solutions, if you do that, you will find something like that starts like this, and then it goes down, and then you see that at some point it will diverge negatively. Then you increase the energy until you find something very accurate that converges, and this is going to be your E1. Now you go on and on with this thing, it will diverge up, right? You increase even more the energy, right? Then as you increase the energy, you find another solution that is more like goes up and then down, and then it goes up again, and it will diverge positively, for example, or negatively. I don't know the sequence exactly, but it will be something like that. So you refine your energy again, you find another solution that converges. This is going to be E3. And then you keep going on and on. In the end, you will find the sequence of eigenstates of your system. It should be like E0, E2, E4, E6. And if you start the procedure with the odd solution, you get E1, E3, E5, and so on and so forth. Okay? So in the end, you'll have all the wave functions and all the eigenenergies, but it takes some time. I mean, this is not the most efficient way of finding wave functions. There are other methods also based on different on finite differences scheme, as I showed in another video here already. But this is, as I said, the good aspect of this thing is that it's very simple, it's very basic. You can, for example, if you have a software like this LibreOffice Calc, you can just put a column for your x-axis, right? And then in the x-axis you put some numbers. So these would be like numbers that you put here would be the values for the x-axis. Then you put another column for the psi. This is what we're calculating, right? So you put another column for the derivative of psi. This is an auxiliary column, right? And what else? You have to put a column for the potential too. So that would be the potential at any point x of your axis, right? And this is also something that you have to give, right? These numbers are already here, the x numbers are already here too. You need to put a cell where you guess what is the energy, right? So you put in some energy in a cell. This is your guess, right? And then you tell your software to plot this function here, okay? Which is, for the moment, in my drawing here, is still not calculated. But let's say that you are going to tell it to plot it here, okay? So what you are going to do is you provide this number and this number. And which are these things? Like if it is an odd solution, then you come here. This one is 0, the other is 1. Then you put like 0 here, 1 here, for example. And then you tell the computer to use this to calculate these cells according to these rules here, right? So you want to calculate this, we will need psi and psi prime at the I point, but to get the psi I, you need to psi I prime. In order to get the psi I prime, you need to use like this delta x and v and so on. So then here you will also need to define another cell with the delta x, of course, because then you can keep coming back to this thing. Or if you want, you can put it in the formula itself. So you need to say something like this number is equal to this one plus delta x multiplied by this one, right? And then this one, I want to calculate it here. So which one is this? It's this number plus delta x multiplied by v minus energy, and then you calculate what is this number here. So from then on, you copy paste this rule, and then you keep the software will calculate these things because of the rule that you just created. And then in the end, you get a function here, and this function will be plotted here, and you see something like, let's say, like this, because you guessed the energy wrong. And then you start doing this thing, and it will be automatically changed. The function here will be automatically changed until you find the correct energy for your solution. So this would be the method. I will make a video later on where I apply these things to I think I'm going to use LibreOffice Calc, and then we see how it goes. But this is more or less the method. If you have let's see, if you have some knowledge on some programming language, this is going to be easy to do. But even if you don't, if you just use your normal spreadsheet software, this is going to be also convenient. And it's at least a good exercise to see how wave functions work in Schrödinger's equation.